Hi there and welcome back. Act 2 in our discussion of joins in relational database systems, chapter 12 of the DB2 course. Alright, this is the slide where we left the last time, and it's the slide about nested loop join, the fallback as it's called here on the slide, and I think that's quite appropriate nickname because this is the workhorse nested loop, join algorithm. It has no restrictions regarding the join predicate. It has no restrictions regarding any sort order of the outer and inner tables. Indeed, it ignores indices on these outer and inner tables, and that's a bummer. But as I told you already, we can fix that. And let's add a few more details to the discussion of nested loops join. If you look at the pseudocode of this algorithm here, this suggests that we indeed iterate over the outer and the inner table in a row by row fashion. So if looking at this element in symbol here, each row O in outer suggests that we indeed iterate in a row by row fashion. That would be wasteful, and indeed this is not how it's implemented inside a real system. As you know, access to the row data inside, the heap file for the outer and inner table, of course, has to be performed in a block-wise or page-wise fashion. And it's no different, of course, in the implementation of the nested loop join. We just cannot afford to perform disk seek and disk IO to retrieve individual rows from heap files. We always have to access entire blocks of data. And this leads to this modification of the nested loop join, which would be the block nested loop join. This is what you would actually find implemented inside a block-based, disk IO-based relational database system, the block-based nested loop join. Well, its API would be just the same, outer and inner table, left-hand side and right-hand side tables, and still no restrictions regarding the join predicate. Internally, we would still generate this join result, initialize it with 0, and then later return it as the overall result. Internally, we would find the nested loop that warrants the name of this entire algorithm, but it would be framed by block-wise access, to the data of the inner and outer tables. All right, so we would indeed first iterate over the blocks BO of our outer table. Each of these blocks BO would carry B sub O rows. Okay, right, so one such entire block BO of rows would be fetched. And then one entire block BI of rows of the inner table would be fetched. This would carry B sub I many rows of the inner table. Once we've done that and have performed these block-wise accesses, these blocks have been moved into the database buffer. Then, only then, we would start the real nested loop join logic, which is specified in a row by row fashion here. All right, so we would pick an outer row from the block that we have just moved into the database buffer, and we would pick an inner row from the inner block, and then perform our join logic here. All right, and we would perform this nested loop comparison of the outer and inner rows in the blocks BO and BI. Once we have exhausted the contents of these blocks, then it would be time to, maybe fetch a new inner block and then repeat this inner nested loop for all the rows in the outer block with all the rows in the new inner block. Or once we have consumed and exceeded all the inner blocks of our inner relation, then it would be time to consider the next outer block of the outer relation. So you see, this is a loop nested to depth 4 here already, but the overall logic of nested loop join is of course still preserved. We only make sure that I/O will happen in a block-based fashion. This indeed will lead to less disk seeks. This is the entire goal of this block nested loop join algorithm. Okay, Well, what would be the number of disk seeks that we have to perform? Well, of course, there is that many rows in the outer table, but we would consume them in block-based fashion. Each of these blocks would fit that many rows. And well, this division here, this describes the number of disk seeks, the number of block accesses that we have to perform on the outer relation. There will be many more disk accesses and more disk seeks on the inner relation. Well, of course, this is the number of iterations in the of the outer block-based loop, and you will find that again here. For each of these blocks, we will perform seeks in the inner relation. Well, not for each row, but only for each inner block of size b sub I. So that would be the number of disk seeks in each inner loop. That many disk seeks in the outer loop. The product of that would be the overall number of disk seeks that we have to perform one such complete inner loop. All right. Okay. So now you would probably ask yourself, okay, so there's only limited disk space available. I need to devote some of the disk space to hold blocks of the outer relation. I need some of the disk space to hold blocks of the inner relation. What would be the best distribution of space inside my block, inside my buffer? Shall the outer or shall the inner relation be preferred in the database buffer? And the answer to this is given on the next slide. This is a computation of the number of disk seeks that we have to perform. So that would be the unit that you will find here on the y-axis of this two-dimensional plot. Well, this is the number of disk seeks that we would need to perform, given that we assign this many blocks, or maybe the percent of space, or whatever have you, a unit of space inside our database buffer to the outer participating table. So this determines the B sub O size, the block size of our outer participating table. How much space is being reserved for the outer table inside my database buffer? The rest of the space, of course, would be available for the inner table, and blocks that we can hold in the database buffer for the inner table, which of course would be the overall database block size, database buffer size minus what we have already allocated for the outer blocks. Okay, so that's why you can see, well, if we assume an overall database buffer size of B of 100 units, say slots, blocks, maybe 8 kilobyte blocks, that's why you can see that in each of these columns, the size of the space that we've allocated to the inner relation and the outer relation always adds up to 100, to the entire buffer size that we are considering here. So 80, 20, or 50, 50, and so on. This is how to read this diagram. And you can see how the number of disk seeks develops as we consider different block distributions between the outer and inner in our database buffer. And of course, we are aiming for the minimum number of disk seeks. And you see that in this area where we use the buffer space in an even fashion, evenly distributed between the outer and the inner participating tables, we can expect the minimum number of disk seeks here. All right, so that would be one answer to this particular question: how to organize the buffer space when you perform block nested loops join. Okay, so that would be one aspect that I would like to highlight here. And then there is a different aspect that is related to the actual plans that you will see when you use the explain SQL command on plans that use the nested loop join. We will of course have a look at such plans in just a minute. But before we do that, let's look at one particular plan operator that you will often find there, and it's the so-called Materialize plan operator. All right. So, well, this accounts for the fact that in such a nested loop join, the inner input is scanned many times. Indeed, it scanned this many times as we have just discussed in the context of the block nested loop join. So we have to reread the inner input again and again and again. And indeed, you can see this in the PostgreSQL plans when you look at the loops annotation that comes with all the plan operators inside such an explain plan. So if you look at the loops annotation for those parts of the plan that deal with the inner input, then you will see loops equals n values for values larger than n. And indeed, this large n reflects the number of times that the inner input has to reprocessed over and over again. So while most of the plan will probably have an n of 1 here, so each operator is, or each plan operator is indeed executed only once, the inner input of a nested loop join will be processed many times, and this will be reflected by large n values in this loops annotation. We will see that in a minute over in the terminal. To help the situation, to optimize this particular situation where some buffer of rows or some amount of rows is scanned again and again and again, to alleviate this situation, there is a dedicated plan operator inside PostgreSQL. This is called Materialize. What it will do, it will evaluate its subplan. So Materialize will be the root of a subplan. The subplan below the Materialize operator will be executed once. That subplan will deliver a batch, a result of rows. Materialize will allocate some internal working memory, maybe a temporary file, but in the best case some RAM resident working memory, to store the rows of the subplan result for later reuse. All right. So this is what's called a so-called tuple store inside PostgreSQL, a temporary storage for the intermediate results that a subplan delivered, the subplan below Materialize. The benefits of using such a tuple store is that it can be very quickly be rescanned, much more quickly than a regular heap file scan that would be implemented by a sequential scan in PostgreSQL, for example. You know that the sequential scan has to perform a lot of work. It has to perform the evaluation of interpreted predicates, for example. It also has to perform checking for the visibility of rows for these xmin, and xmax values that we have discussed in the very beginning of the entire course. All of this would be tasks that sequential scan is burdened with. Materialize would make sure that this task is only performed once. So predicate evaluation is performed once, xmin, xmax checking, and all other kinds of administrative stuff is only performed once. The resulting rows are stored in the tuple store, and when the evaluation of a nested loop join requests the rescanning of an inner input again and again, we will just simply scan the rows in the tuple store and not re-perform the sequential scan on the heap file again. In the tuple store, we are certain that the rows are already fulfilling or satisfying the given predicates. They are only visible rows that have already undergone this in, min, xmax checking, and so on. So scanning the tuple store is much more efficient than re-performing a sequential scan again and again. So the constellation that you will find in the pre-read plans would be just as described. You would find a Materialize operator just above the subplan that will compute the inner input of our nested loop join. Of course, the Materialize will be asked by the nested loop join to repeatedly reproduce the rows of the inner join input. This will not change, and we will find a loops equals n here, probably with large n. Below the Materialize, the subplan below the Materialize will only have an annotation of loops equals 1. We will evaluate the subplan once, pay all the sequential scan costs only once before we save the rows in the tuple store, and then reproduce them at a very efficient cost, very low cost, n times. All right, so many words for rather simple concept, I would say. Let's switch over to the terminal and see how the join playground fares over there. All right, so that would be the playground here. Let me clean up the mess. All right, so this would be the one and many playground tables that I've already described in the last video. Here you can see the schemata. You can also see that indeed, the many table refers to, well, the rows of the one table. Indeed, many rows in the many table may refer to one row in the one table. It's a true 1-to-n relationship as described in the last video. Well, we've got some indices, the primary key indices defined on these two tables, and then we've populated the table. There is the one table, which would be the left-hand side table in all of our examples. It's the smaller table, which only 10,000 rows. Okay, if you recall, the C column of each row would describe the number of join partners that are expected on the many side. Okay, so yes, you can see this will be a random value between 0 and 100. So indeed, there will be from 0 up to 100 join partners in the many table for this particular one row. So it's a true 1-to-100 relationship that we are preparing here. Okay, so 10,000 rows in the one table, and then we would just check the one table when we populate the many table, check how many join partners are to be defined here, and then produce just that many join partners here on the many side. All right, so if this is a random value between 0 and 100, well, we would probably expect an average of about 50 join partners over here on the many side for each one row. And I think we can indeed see that. So what I'm doing here is just I'm checking all the one rows and their C column, which would just report the number of join partners on the many side. And if I evaluate this particular query, then you will see, well, indeed, so 50.6 rows on average join on the many side. Okay, let's quickly look at table contents here. As expected and as described, this is a 3-column table with primary key A. Well, this is the number of join partners on the many side, and you can see, well, all right, you can see what we have indeed observed and expected here. And then here's the many side. The many side of things, and of course many such rows indeed join to the same one row with key value A equals 1 on the left hand side of the join operation. And we have indeed numbered all the join partners here in ascending fashion in their C column. Well, in this example, we also have the rightmost and the leftmost part of the split up MD5 value that encodes the A column here, and this would lead to an alternative join predicate to reassemble the rows of the one and many tables. Okay, so that's just a repetition of the playground setup that we have already described in the previous video. Okay, so now let's look at the effects of Materialize here in the evaluation of nested loops join. Okay, we have just seen input tables. I don't think we have to look at them again. So this would be just one such join between the one and the many table. Okay, here's the predicate that determines which rows are indeed join partners, but I invite you to have a closer look at this particular predicate. It actually consists of 3 parts, of 3 conjuncts. So if you look at this particular part, it only talks about the C values in the many tables, m.c less than 2. And this is indeed not a join predicate. It's a predicate that could be locally evaluated on the many table alone. And we would really hope that the system is clever enough to restrict the number of M rows that flow into the join operation before the join actually starts its work. So we expect this predicate to be evaluated early. Once we scan, or while we scan the many rows, we would probably discard all the rows that have a C value of 3 or larger. And this same on the one side. This is a predicate that could be locally evaluated on the one table. And we expect the system to do that and not burden the join operation with all the rows that will be discarded from the entire query result anyway. Only this part is the true join predicate. It refers to the row variables O and M here and can only be evaluated if we look at combinations of O and M rows here. So that would be the true join predicate. As you can see, it's a less than predicate, which would be a perfect job for our nested loop joins, which can deal with any join predicate and comparison operator type whatsoever. All right, it's a true theta join here. All right, so let's look at the plan that PostgreSQL decides to generate here. Okay, that took some time, almost 10 seconds. Right, so let's look at the plan. Let's first look at the top and let's check that indeed a nested loop join has been performed. Yes, okay, so this would be a nested loop join. And the join predicate has indeed been identified. It's only this part of the entire where clause. It's the OB less than MB part, which is exactly the part that we have highlighted before here. Only this predicate is relevant to identify join partners. All other parts of this where clause have been evaluated early, before the join actually started its join work. All right, so that would be the nested loops join. So let's look at the inputs of the nested loop join. It's a binary operation. It of course needs 2 inputs. And we find the 2 inputs here. This would be the first input. And this would be the second input. All right. Right. So these are the 2 join inputs. This would be the left-hand side input. So the first input that you would see listed here in such plans under nested loop join, this is the left-hand side or the outer input of our nested loops join. As you can see, the system has decided to make many the larger table, to make many the input of our nested loops join operation, and this has been expected. As I told you, it's probably worthwhile to consider the smaller table, in this case the one table, to be the inner input, because it would more easily fit into the working memory, and that's crucial because we have to rescan and revisit the inner input again and again. All right, so indeed this is the expected assignment of left-hand and right-hand table in this particular join. Okay, what we see is that indeed the system has been clever enough to locally evaluate the predicate on the many table before the actual join work starts. So when the sequential scan generates its output and delivers it to the nested loop joins, all the rows that cannot satisfy this particular filter have already been removed. And you see there's quite the number of rows that have been removed here by the filter. What we can also see is, yes, that the outer part of this nested loop join is only evaluated once. This is what we expected. There is no repeated iteration of the rows of the outer table. The outer table is evaluated once and scanned once. There is no need to evaluate it many times. This is different for the inner input. The inner input is indeed the Materialize, and if you look at its loops annotation, it says 19,789. This is the number of times that the evaluation of the inner plan, of the inner input, has to be performed. So that would be the number of times that we have to repeat, the sequential scan of the inner input, in this case of the one table. All right, to save itself from this burden and this effort, the system plans for a Materialize operator at this particular spot, just as we described on the slides. and it makes sure that everything below the materialized, the subplan below the materialized, is only executed once, and you can indeed see that here. The subplan below materialize in this case, of course, is a sequential scan of the one table. We have to get hold of the other join partners. Okay, so the inner input has been elected to be the one table, the smaller input. Of course, the sequential scan will perform the local predicate evaluation to make sure that only very few rows indeed survive. You can see this indeed only 156 rows could satisfy this predicate. This is the very neat, very small inner input. All of these rows have then to be placed in working memory, and you can see that Materialize has some buffer interaction, has some buffer operations here to place those rows that qualify into pages of the buffer. They will be kept and then rescanned by the Materialize operator whenever the nested join requests the access to the inner input. Okay, so, but the crucial thing is this: we don't have to redo the sequential scan of the inner over and over again. All right, so that would be the evaluation of a nested loop join using Materialize operator. And well, what we've seen here on a very busy system, busy with video encoding, this took almost 10 seconds. So let's see what happens if I disable Materialize for a second here. I don't think that's a very clever idea, because this leads to rescanning of the one table of the inner input over and over again. So let's do that and disable Materialize for the next plan. You see that this is the identical query that we have just considered. Let's re-evaluate it here. And then wait. Okay, this took its time. 35 seconds for a nested loop join plan that, yes, indeed has not used a Materialize operator here. All right. Okay, so this is the value of Materialized in the evaluation of the nested loops join. Okay, so let's quickly re-enable the Materialize here. All right, so that we don't suffer these waiting times in our upcoming discussion of well, further details of nested loop join. There is one more variant of nested loop join that I would like to discuss with you, but this is something to be saved for the upcoming video. Hope to see you then. Bye-bye.